All right. The first part of what we'll talk about in the class is physical hydrology. So we made the case last time. This is what we'll talk about today. We'll go through each of these things in sequence. But we made the case last time that we're choosing to deal with solvents in groundwater, non-aqueous phase liquids in groundwater, gasolines and diesel fuels, which are lighter than water and float, solvents such as TCE and TCA, which are denser than water and sink through water. And the behavior that we're interested in is conditioned by the behaviors of these components in groundwater. And so one way to think about this, if I plug this in, I guess that'd be useful. Is it not thinking yet? Yeah. So we are on topic 2, part 1. So it's physical hydrology. So I don't know why this is not working today. Bad handwriting, right? Well, no, that's better. So this is my hopeful remedy to stop you, to engage you. So to make you follow what I'm trying to get over. So here's the idea. So you have ground surface. You have a water table that sits below the ground surface. Above here is kind of partially saturated soil or rock. And below here is everything, all the pore space is filled with water. And below this you may have a different bed, such as maybe a shale. Something that has very small pore space in it. Shale is just a low permeability rock. And the idea is that you, on the surface, you spill something, maybe in some of these 55-gallon drums, and it goes into the subsurface. The behavior that you get, depending on this, these are going to be horrible figures, but I'll try and at least slow it down so that you can keep up with the points I'm trying to make. And that is, independent of this geometry, if you have this geometry and a fluid which is lighter than water, so a light non-aqueous phase liquid, then the behavior you get would be different if you had something which was denser than water. And the behaviors that you get out of these are the behaviors that you see that we'll go back to the sheet to look at. And that is, if you have this geometry with the sloping groundwater table and a bed under here, which in this case we don't particularly care about, is what will happen is this stuff will be happy to go down through here. It will kind of percolate down through here. When it hits the water table, which is filled with pore fluid below here and basically filled with air above here, what it will do is it will tend to sit on here as a lens. It will slightly depress the groundwater table. And so this will be basically 100% gasoline, if you like gasoline. Up here will be this kind of column of smear that it's gone down through, that's left some of its tracks as it's gone across here. But once it gets in here, it's actually buoyed by the water, and because it's less dense than water, it can't actually sink through it. It doesn't matter that it's in a porous medium where it's only going in the pore space. It'd be the same as if it was on a swimming pool and you put gasoline in a swimming pool, you'd get this fine sheen on the top and it would sit on the top. Exactly the same mechanism. So it would happily sit there. It would probably get down to this depth within a few hours to days to weeks to months, and it really wouldn't go anywhere once it's there. But what it would do is it could dissolve in the water, and because if the water table is going in this direction, and therefore the hydraulic gradient is a positive hydraulic gradient, and we know that velocity by Darcy's law is equal to minus hydraulic conductivity times the hydraulic gradient, and that velocity is a vectoral quantity, then this, in terms of if this is the x and y or p coordinate system, a positive gradient, this is a negative gradient, right? A positive gradient would be this. This is a negative gradient. So a negative gradient times a negative gives a positive velocity. So it's saying that the flow velocity in this is going to be to the right, and we could calculate what the magnitude would be if we knew what the hydraulic conductivity was, a physical property. So this would be happy to stay there, and it would really be no problem at all, except what it's going to do is it's going to dissolve in the groundwater. And as it gets dissolved in the groundwater and diffuses away from this interface, it gets picked up by the motion of the groundwater that's flowing past it, and it gets carried downstream as a plume. That's basically the mechanism by which it will move. And so that behavior is significantly different from the behavior that you get if it's denser than water, where if you basically have the same kind of geological situation that you had before, now as you drop this stuff through here, yeah, sure, you get this nice little column as it percolates down through here. There's no reason why it should stop here. It's like dropping a ball bearing, I guess, in a swimming pool, or anything that's denser than water will slip below the surface, and so it won't stop. And bless you, and then what it will do, bless you, it will leave a track, and it will do something like this. And the plume now that you'll get here, take your favorite DNAPL, whatever it is. Trichloroethylene is a dry cleaning solvent that's kind of a favorite bad actor, I guess. So the behavior is slightly different. Now it's not been stopped by the water table. It's not been influenced by it very much at all. It's sitting at the bottom. Still, the water will be happy to flow through here. There'll be this column here that is kind of a chimney, often referred to as chimney, which will have a lot of void space in it, which will be filled with water. And so, of course, this water that goes from left to right as it goes down here will do exactly the same as before, and you'll get a plume that will develop, and the front of that plume will be here at time t1 and time t2, and at time t3 it'll just keep on moving to the right-hand side. And so if you have a water well which is dug into this over here, where you're pulling out water, then when this gets over here, obviously it's a problem in either of these cases. So there's some significant differences between these two behaviors where it's lighter than water and denser than water. But there are also some reasonable similarities between the components that you have. Each of them have this kind of chimney which is mainly filled with air, got a little bit of water in it, and a little bit of gasoline or TCE. And of course this can volatilize and vaporize and come out of the ground with time as well. In this case, all of the free product, the gasoline itself, is basically cupped and buoyed on the surface of the water, which it physically can't get below because it can't sink below. It's like oil and vinegar in a salad shaker. And the only way that it can move in the groundwater is to dissolve in the groundwater and be carried downstream. Where this material here is basically 100% filled with water with a little bit of stuff as dissolved material. Not free product. This is what we'll call as free product, which means it's in its free phase, not vapor phase. And it will dissolve in groundwater and be carried downstream. This has exactly the same chimney with mainly air, some water, and a bit of TCE. This will be mainly water, no air, and a little bit of TCE, which is just the smear that gets left as it goes down through here. And this will keep on going, as we'll find out, to the center of the Earth if it's not stopped by something. And it has to be stopped by something, and bless you, this something would be what we'll refer to as a capillary barrier. Not because it has low permeability, but because it has small pores, which we can't get into. And so I say that when we talk about DNAPLs, it's the most, or NAPLs, non-aqueous phase liquids, it's the most difficult problem to solve, is because we have to talk about multiphase flow in getting to where it starts to dissolve from, and then on top of it, talk about the dissolution of this in groundwater and the rates at which you'll travel downstream. So we have to solve this problem first to know what this will look like before we know what the plume can look like. And so if we want to solve any of these problems, we need to be able to know exactly what this initial state will look like as a prerequisite of doing anything. So that's why it's kind of a challenging problem to deal with. And so this figure explains exactly that. This is the zone where you have this smear. You can't really see it very well here, but this is a lens that sits on top of the water table, which does something like this. This would be the smeared area. This would be vapor in the gasoline vapor, which would be volatilizing off, and it would work its way up through the partially saturated zone and come out of the surface in some small quantities. And the only interaction that the free product has with the water is in this kind of zone here, where it can mix with it, and ultimately where it can then be carried downstream because the water table is saturated. The other thing that you probably know from your 452 class is that the saturated zone is overlain by what's often referred to as the tension saturated zone or the capillary fringe. And so this is a region where this is 100% filled with water, and this is where, and the water pressure at this point is equal to atmospheric, which is by definition the definition of a water table, and we often use this little triangle to denote that. The water above this is actually in tension. So the water isn't just at the pressure of the atmosphere, it's at less than the pressure of the atmosphere. And we'll talk about the reasons for that in due course. But when this lens comes down through here, basically what it will do is it'll kind of flatten out this tension saturated zone and remove it so that the water table now looks like basically the base of this zone here, if I can draw that. So, okay. And you see exactly the same behavior here. It's the same idea. So a smeared zone, it's gone right through the capillary fringe or the tension saturated zone, hit the water table, kept on going, and now you have a component that sits here. The free products, of course, even though it's sitting inside porous medium, it's no different than pouring this on the windshield of your car. It won't travel uphill, it'll go downhill. And so the other significant feature of this is that this is just rolling downhill to some degree until it comes to rest, until it doesn't have any more volume to be able to do that. But the transport of this with the groundwater flow going up here will actually take this and it'll take the plume from here at time 1 to time 2 and to time 3. And this plume will just be the stuff that's dissolved in groundwater. And so that's the problem that we want to solve. And so the first step in being able to do that is to be able to solve the initial problem of how this stuff travels in the unsaturated zone. So that's our first step. And so that's what we'll deal with. I was going to say something else. Okay, so other things. NAPL, apparently NAPL, the word comes from the Love Canal litigation, where, which is in upstate New York, the first groundwater contamination problem in North America, where a bunch of barrels were dumped in Love Canal and a housing development built on top of it. And NAPL was apparently something that the lawyers who are defending the Hooker Corporation came up with because it sounds like apple and therefore is less threatening and therefore is a nicety. I don't know if that's urban myth or not, but that's supposed to be the case. Okay. So you can imagine all kinds of questions that we might want to answer. I guess they would be things like how quickly does it take to get down to the water table? Is it hours? Is it days? Is it years? Is it millennia? We don't know that yet. What would be the saturations of the material in this smeared zone, and what would be the saturations within this zone? Are there reasons where it wouldn't go into the ground whatsoever? And what are those conditions that it wouldn't go into the ground whatsoever? What are the conditions by which it would actually stop at some kind of barrier? What are the properties of that barrier that would force it to stop? Is it because it has low permeability? It isn't, but it turns out to correlate with the reason for it having low permeability. Or is it some other property? And so those are the kinds of questions we'd like to answer, because one, we'd like to know where it would go in terms of prediction if you have a spill, where you should look by drilling into it. And we'd also like to know how much material we're going to have to remove from the system to be able to remediate it. And I suppose we'd also want to know how we should remediate it. And the reality is that if you don't take out the source material, which is often a preferred reason of remediation is to not remove the source material, But if you don't remove the source material, you'll be remediating it forever, because basically these components are toxic of the order of parts per billion, and you can certainly supply parts per billion from a very small volume of material for a very long time to come in a reservoir or an aquifer where you have decent flow rates. So we'll have a variety of different questions we want to ask. So that's kind of where we're going with this. So the first behavior in this zone that overlays the water table is controlled by capillary behavior, capillarity. We've talked about what these look like. I guess there should be. So the other thing is this reader that we have, which you see labeled here, is on Angel, and I update it every time I add something. I added these just last night, so it is 70 megabytes, but it will slowly be updated with these kind of inserted sheets as it makes sense if you want to keep on downloading it. So we've talked about this, so let's kind of define some terms that allow us to be able to look at. So the basic idea is we'll look at what are the terms that we need to know to be able to understand something about this. We'll talk about what controls the behavior of liquids on surfaces, because any porous medium is just a bunch of beads which have surfaces which this other stuff will contact. And so one easy way to think about it first is not worrying about it being beads, but being just a windshield, if you like. And then once we've done that, then we can start looking at models which allow us to look at perhaps granular materials, which instead of thinking of them as a whole collection of little grains which define this material, we can make life easier by thinking of these grains as a whole bunch of capillary tubes. And these whole bunch of capillary tubes have some behaviors which we can relate very simply to some simple analogs and use that to understand exactly how real materials will behave. Okay? So that's where we're going. So here's the idea of this. I'm going to skip through this. So definitions, what do we need? I could probably make this bigger. So the notes for this, if you're interested in finding out a bit more about it, the text by Jacob Baer is one that goes into it in much more detail than Feder. And so most of the material that we'll talk about in capillary behavior in this class has come out of that. So if you're interested in learning more about it, then look at this. So what do we mean by these fluids? Well, you know this, right? The difference between miscible displacement and immiscible displacement is that in miscible displacement, the fluids mix, and they can be, one can be dissolved in the other. And so typically, the example I give of that is taking a beaker, and into that beaker you put a drop of ink. And if you drew a profile of concentration, so you take a beaker and you drop in it a drop of ink, and you draw a profile across that drop of ink in terms of X versus concentration, and this is exactly what you have here. So if you look at that drop of ink and what the concentration is, it starts off with initially 100% concentration here, 0% outside, which is water. And what you know from Fick's law is that nature abhors an infinite concentration. So the concentration gradient here is infinite, and so it will drive a mass flux. And what it will do is it will try and get rid of this infinite gradient, which is this line here, and it will make it into a flatter, it'll be this bell curve which spreads out. And at time 1 or at time 2, as it gets flatter and flatter, it will slowly move out. Until, as you know, your beaker will basically be a mixture of ink and water all mixed together at some uniform concentration. If it is oil that you drop in here, then that won't happen. It will stay as a separate fluid. And basically that's the case that we're dealing with in this initial part in talking about these fluids. When we talk about real materials with porous media with water in them, we need to define things in an appropriate way. And so what we'll find out that there are a couple of important parameters that we'll use. One is called capillary pressure. And that is referred to as P sub C, which is the difference between the pressure, by definition, in what's referred to as the non-wetting fluid and the fluid pressure in the wetting fluid as a result. And we'll talk about that a little later. And the other term, which is perhaps less abstract and esoteric, is saturation. So saturation just refers to the amount of fluid that fills the pores, which is of a particular kind. And so by definition, the saturation of phase A, so this is phase alpha, right? This is phase alpha. So the saturation of phase alpha is the volume of that fluid within the volume of voids within the REV, the representative elemental volume. Elemental, which is just a very fancy way of saying a bit of porous medium that's representative of all your aquifer. So you take a porous medium that has enough pores in it that's representative of your aquifer, and that's your volume. You look at the proportion of the pores that are filled with one fluid relative to the volume of those pores, and that percentage, usually written as a decimal, is the saturation of that. So it's the volume of fluids versus the volume of voids. So if you have water, which is, or a porous medium, which is 60% water, 20% air, and 20% napple, which, for instance, it might be in this chimney that goes down to this lens of stuff as you drop the stuff through the porous medium, then the saturations of those would be, the saturation of water would be 0.6 or 60%. The saturation of air would be 0.2, and the saturation of napple would also be 0.2. So straightforward. I make that point because depending on the background you come from, so flow and porous media has grown up in a variety of different disciplines. It's grown up in petroleum engineering, it's grown up in groundwater hydrology, and it's also grown up in soil physics. And each of those disciplines have their own vocabulary because they've actually grown up separately and now converged that all the principles are the same. But if you talk to a person who does soil mechanics, then looking at unsaturated flow or soil physics, then it's usually done on a volume basis again, but the volumetric moisture content is the volume of water, again in the porous medium, relative to the total volume of that piece of soil, the solids and the void space combined. And so if the porosity is equal to 30%, so you all know what porosity is, right? Porosity is equal to the void space divided by the total volume of the soil cube that you have. So everyone knows these definitions? Not know them? Does not. Yeah. Then if the porosity is 30%, then if it's 100% saturated with water, then the volumetric moisture content would be 30%, right? Because the void volume is 30%. 100% of that void volume is filled with water. So 30% of the total volume of that is water-filled relative to the total. Right? And so you need to be aware of those different terminologies. We'll use these two terminologies. We'll use saturation and we'll use volumetric moisture content. We'll use both of them. In soil mechanics, the terminology for moisture contents is in the weight of water relative to the weight of solid. So it's just another different definition. We won't use that, but you should be aware that there are these different definitions. And the other thing that's important in this, which I didn't make the case, but you should realize, of course, is that the saturation across the phases, so if the saturation of the water plus the saturation of the air plus the saturation of the napple in this case should add up to 1, and they do. So in other words, the sum of the saturations are equal to 1. So in other words, this 1.0, right? So straightforward. So we need to understand that because that controls the things that we're talking about. All right. So I'm not going to go through those. So we made the case that the first thing we'd like to be able to understand is how this stuff behaves on the windshield of your car, because that's the easiest way for us to understand. Of course, actually, let's step back one from that. And the easier way to think about it is in terms of how it would behave not on the windshield of your car, but if it's just two fluids in contact with each other. And so if you think of the case of salad dressing, where you have water, I guess, over oil, I guess it would be this case, right? So if it's salad dressing, this would be water, which is denser than olive oil. Last time I checked. This would be olive oil. And you have gas above that, which is the atmosphere. If you look at the interface between these liquids, you could imagine that there is basically a triple point, not in terms of a triple point in terms of a phase diagram, but in terms of a triple point in terms of where these components meet. And if we're talking about interfacial tension, the forces that act between fluids, they only act at the boundary between the fluids. Away from the boundary between the fluids, there is no interfacial tension, there is no force that acts. They only act at the connection between those fluids. And so if you look at this point between these three fluids, then you can draw a diagram where the connection between these fluids is just driven by a force diagram, which is the forces that act at the confluence of these three fluids. And you can basically do an equilibrium calculation to see whether the force pulling this boundary here to your left is bigger than the force pulling them to your right. And if the force pulling them to your left is bigger than the force pulling them to the right, you'd expect that this would take a thin layer which would cover the whole of the swimming pool, and you'd have the air above it, you'd have the gasoline on the water of the swimming pool as a sheen, and you'd have the water underneath. Or if the force pulling it to the right is larger, then it would sit on the surface as a blob and wouldn't get bigger than this blob, which would have some height attached to it. And so I don't think we need to belabor the point, but you can take this and you could do a free body. You can resolve forces in the x direction, and of course the forces in the x direction acting to your left is this magnitude here, the force acting to the left. And the forces acting to the right are due to the interface between the gas and the liquid, which is this one here, multiplied by this value here, right? So this is sigma bg cosine theta bg, nothing more than that. So you're just resolving. So that's this magnitude here. Likewise, you do it for this force here, which is due to the force between the oil and the water, and you have these four components. And so if you wanted to, should you want to, then you could make a determination whether this would sit as a sheen on top of the swimming pool or a blob. If you knew what these interfacial tensions were, if you took this cosine value to be a very small number, which is basically 1, so in the limit this will go to 1, right? The cosine of this. You can make it 1. And if you know what the interfacial tensions are of these interfaces between these two fluids, which is a fundamental property which you can go to a book and look up, then you could figure out how it would sit within this on the surface of the fluid. Whether it would sit as a sheen that covers the surface of the swimming pool, or whether it would sit as a blob. Okay? And it's just depending on whether the force pulling it to the left is bigger than some of these other two forces. That's all. So, fine. You won't have to reproduce that in anything we'll do here, but it's useful to at least understand the concept. So now if you put the same stuff on top of your windshield, and your windshield is now a solid or a glass plate, you have the same oil that's present on the top, and you have another fluid. It could be gas or a liquid that sits on the top. This could be water, or it could be a gas. It doesn't really matter. And you can basically do the same calculation. And what you can do is you can calculate the same force body diagram as we talked before. Won't go through the points to define that. And you can make the same calculation as to whether this will sit as a bead of water on your windshield or whether it will completely wet the surface at a very thin depth layer. And it's important to know that because you can imagine that if you're trying to push fluids through a porous medium, and of course quartz is basically glass beads, is it basically behaves as a glass surface that you're trying to push stuff through. And if it's not going to spread very easily across this medium, then you're going to have a lot of pressure to apply to push it across. And so if you're worried about whether it goes into the porous medium really easily, it's probably a good thing that it doesn't, if it doesn't wet the medium very easily, because it won't go in very easily, so you don't have to worry about the transport. And so all of these behaviors are predicated on whether we can actually wet this surface. So what you need to know from this is not so much how to be able to resolve these forces, the fact that you could resolve these forces if you so wanted to, but more the case of the fact that the behaviors that you get would be different if this is able to completely wet this surface or whether it's stopped from wetting the surface. And so the other definition that we need to deal with in terms of properties that control this behavior, the first property is knowing something about surface tension. Surface tension is the tension between a liquid and the vapor above it. And interfacial tension is the tension between two fluids, two liquids, I guess. But if we know what these properties are, and you can look them up in text, handbooks, and we'll supply them in this class. If you know what these properties are, you'd like to know whether you can calculate exactly what the behavior would be on this glass frit, which would in some way be some indicator of how it would behave in the subsurface. And so what we define is another term, and the term is wettability. And wettability refers to the ability of a liquid to be able to wet, quote unquote, a surface. And so the terminology that's used is that you look at this angle that is defined by the shape of the bead that sits on top of this surface. You always measure this angle just by convention from the densest fluid. So it goes from the densest fluid, and the value here would be 0. This would be 90 degrees, and this would be 180, obviously. And in terms of the definition here, if the angle is less than 90 degrees, then this fluid is said to wet the solid. And so wetting the solid means that it can try and move relatively easily across it. So most sands in petroleum reservoirs, most of the aquifers we'll deal with are what are referred to as water wet. They'll be wetted by water. Water will be basically sucked into them. So you put a bead of water on the surface, it'll just disappear into it because it has this affinity to be able to claw itself. It's attracted to the surface, and therefore it wants to be able to move across here. If the angle of attraction between these is 90 degrees, in other words, basically, what would that look like? I suppose it would look like this. It would look like a blob that sits on the surface like this, right? So this is 90 degrees, and this is 90 degrees. This would be water, or soaps. This would be the wetting fluid. And it'd be 90. This, in other words, it would just take up this region here, and a fluid which is the opposite. I guess this one's this one, and a fluid which does the opposite, which would have this. So this is the denser fluid, and this is the bead. This is the less dense. So I suppose this could be a bubble of gas, for instance. So if the bubble of gas existed in here, getting a cramp in my finger, then this angle for sure, which we measure here, is what? It's 120 degrees or something in this case. Then in this case, the gas would be the fluid that wets the surface, right? And so it's defined basically by the angle which is less than 90 degrees. So in normal cases, this would be the bead of water. This angle here is 45 degrees, say. The water wets the solid. In this case, this gas wets the solid because the angle is now larger than the 90 degrees. Fluid used, this is the non-wetting fluid. Okay? And so you've seen this in fluids for sure, right? If you push a capillary tube into water, then you see that behavior. And if you put a capillary tube into water, the behavior you get would be the water rises in here to some height, and in 303 we call this H sub C. If you put a capillary tube into mercury, it does the opposite, and it would do something like this. And this would be negative Hc. This would be in mercury. And so depending on, usually with this behavior here, right? So if you blow this up, you have this. This is less than 90 degrees. This is wet. This is gas. And so in this case, as is usually the case, water wets glass surfaces. And as quartz in many reservoirs is basically glass, then most reservoir rocks and most aquifers which contain quartz are also water wet. I guess the exception to that are things that are made from limestone. Carbonates are often not water wet or oil wet reservoirs. So this is just making that note here at the bottom. There are different cases. Usually water is a wetting fluid in petroleum reservoirs. Usually water is independent of whether the other fluid is petroleum, a liquid, or air. And in most of the cases we will deal with water as the wetting fluid for these other non-aqueous phase liquids as well. Okay? So if we go back to kind of where we're coming from in this, we've made the case that we know something about saturation. So we know what saturation is. We've kind of defined capillary pressures, although we don't really need to use those yet. There's a difference between the fluid pressures in the two different fluids that we have in our system. We've talked about how these affects behavior both on fluid-fluid interfaces and also on fluid-solid interfaces. And so now the question is how we say something about how that would behave in porous media. And before we go and talk about that, the easiest connection to make is that when you're talking about porous media, of which this is a really bad diagram, but you get the picture. This is actually a blown-up diagram of some experiments, kind of classic experiments that are done by a guy called Frederick Schwiller, who dropped napples lighter than L napples in this particular case into basically an aquarium tank full of soil with water in it, and looked at the transport of these napples as they went through this partially saturated zone, and then blew up portions of them. And what you see here is a whole bunch of beads, where the beads are in contact with the wall of this aquarium. And you can't see it very well, but there's a contact between the non-aqueous fluids. You can perhaps see it better in this, in that there's a pathway that this fluid has chosen to take, which is kind of wound down through these beads. It hasn't gone through all of the connections, right? It hasn't gone through this connection, for instance. So one question might be why. This one's kind of stopped here instead of keeping on going down through these gaps between here. And again, the question is, why is that? And so one way that you can actually get a stab at why this behavior might occur is to think of a really straightforward analog to understanding what this porous medium can be represented as. And so the first analog that you could apply would be to think about a capillary tube. Okay, well, perhaps I won't do that yet. Yeah, perhaps we'll talk about a capillary tube. And what this allows us to do, again, if you've taken a fluids class, you'll recognize this. It's exactly the geometry that we've looked at previously. And the basic idea is this. What we'd like to do is we're going to take a porous medium, and this porous medium happens to have a whole bunch of solid grains in it. And these solid grains, I describe a pore in it. And so if we blew up this connection between these solid grains, and I can do it well, I guess I didn't blow it up very much. You could think of this pore, and I can't use a different color here, but I guess I could do this. You could think of this pore as having an equivalent radius. I've probably drawn it a bit big. But think of this as a little capillary tube which is present within this pore. And we think that the kind of constricted shape of this pore is something that stops these non-immiscible fluids from being pushed through the system. Right? You can imagine trying to push a bubble. Perhaps the easiest analog is if you had a straw filled with water, which is representing this pore throat, and you tried to blow air into it, which is another immiscible fluid. The force you have to apply to be able to push the air out of this is governed maybe by the amount of fluid that's in there, but also as the tube got smaller and the interfacial forces got larger, it would actually be the resistance of the interfacial forces which would be stopping it from moving out. And so what we'd like to be able to do is to be able to represent this porous medium instead of as being a whole bunch of gaps between these pore throats. Instead, we can represent it basically as a bundle of capillary tubes. And so if we know how one of these capillary tubes behaves, then we can look at all of them together and we could make some suggestion as to what the controlling features would be if we look at behavior of a porous medium. And so the easiest way to look at this is to basically look at a capillary tube. And so here's the idea. This is a capillary tube. You put it into water. It rises up to some height. You can do a couple of things, right? You know for sure, since the pressure on this surface here is atmospheric, as it is on this surface here, if you go across a fluid and you're on the same elevation as you go across that fluid, then you know that this point here also has to be atmospheric pressure as well. If you know that, then you could actually cut off the bottom of this tube, and you could make a tube that looked like a free body, which is this, where this is the height of the tube, this is its diameter. You have to apply some kind of force here to be able to lift it up, and you can resolve the forces on this. And so what we're doing is you're just cutting off the bottom of the tube, picking it up, and seeing if we can balance the amount of force that we have to apply here in the vertical direction versus the weight of the fluid which is coming down here. So that's all we need to do. So two things. We know that this is atmospheric pressure. We know that since we can go from this point to this point here, which is on the same horizontal line, so this has to be atmospheric pressure. We can therefore cut it off at the bottom and represent it as this. And now we can treat it as a free body, and we can just balance forces. If we balance forces, then what are those forces going to be? What's the weight of this? Well, let's ignore that this is a dip here. Let's think of this whole volume that we have here. So pi d squared upon 4 is the cross-sectional area. The height of it is the cross-sectional area times the volume. So this is the volume of that. The unit weight times the volume together is going to be the force acting vertically. And we equate that with the force acting upwards. And so if this angle here is theta, then again, just from a free body diagram, this is the force which is due to the interfacial tension, which is going to be this times the length. This is the circumference of this. So if you're looking down on this thing here, this force, the interface acts at everywhere around this circumference. And so you can just multiply the magnitude of this force multiplied by the circumference, this gives us a total amount which is F. And if this is theta, then this is just F cosine theta. And so that's all this is. And so we've done this before. So what we're interested in doing is just rearranging that in terms of the one parameter we'd like to know. We'd like to know how high it would like to rise up in here. And if we rearrange things, we get the height rise, and we see that it is proportional to the interfacial tension between the water and the solid. We can probably throw this away. Let's just throw it away for now. And it's inversely proportional to the diameter. So the smaller diameter, the higher the height rise, we know that. Go ahead.
Where do we get like the cosine of theta?
It's because we want to do this. So the force that we're applying is in the direction of this interface, right? So this force is actually aligned. So this interface slopes up here, and if you draw this force merely as the extension of this, this is this force. That's the direction of the force. But we want to know, because we're resolving vertically, what the vertical component of that force is here. And it's this magnitude. I haven't drawn it very well. It's this magnitude here. So it's just this. Okay? So it's just this force times cosine theta. It's just a component of this force vertically, if this is a right angle here that intercepts this. Okay? And so it's directly, so the higher the surface tension, the higher the height rise. The smaller the capillary, the higher the height rise as well. And so that's just the relationship. And so in some respects, if you're trying to blow a bead of water through a tube, this is physically the force you have to apply to be able to overcome the resistance of the water in the tube that sits there. And so if we think the tube is really representative of one of these pore throats in our porous medium, then at least we have a relational, a way of defining how we think the behavior should be. We know that if we get really narrow pores in our porous medium, we're going to have to apply a big push to be able to force the fluid through there. And that's not much of a problem if you're in a petroleum reservoir, because you have 5,000 feet of overburden there to build up a big pressure. But if you're sitting in a surface reservoir where the only force that drives this thing is its self-weight, then these forces are relatively large compared to the self-weight of this, as we'll find out. So this is important. So the take-home message from this is that this height rise is directly proportional to surface tension, interfacial tension, and inversely proportional to the capillary diameter. If we define a pressure between the non-wetting and the wetting fluids, as we said already, we defined this parameter of capillary pressure as the difference by definition between the non-wetting fluid pressure minus the wetting fluid pressure. Then in this particular case, this would be the pressure of the water would be the pressure here. This would be PW, the wetting pressure. And the pressure of the non-wetting would be the pressure of the air. And so this would be the pressure of the air anywhere, if you like, but actually just above this interface. So what this is saying, it actually says that the pressure in the water on this interface, there is a capillary pressure. It's not the same as the air pressure. And the reason it's not the same as the air pressure is you have this basically a catenary, which is in tension. So you're thinking of, you have this horizontal surface of the water, you lift up the sides of it so it's in this bowed shape. The air pressure above it is atmospheric, which we're taking as zero. The pressure in the water above that will be less than atmospheric. It's in tension. And so the magnitude of this capillary pressure is actually really equal to, what is it? It's actually equal to the capillary pressure, PC, stop moving, is equal to this height rise multiplied by the unit weight of the water. So in other words, you could think of this as, well, you know it from fluid statics, right? We've said that the fluid pressure here has to be zero because it's atmospheric outside and it has to be atmospheric here. You know as you go upwards in a fluid, the pressure decreases. So it starts off with atmospheric pressure here, then by the time you get to here, it must be less than atmospheric pressure. The density of the air is so small that basically the pressure in the air here will be the same as the pressure here, and so this is going to be in tension relative to this, and so there'll be a difference between those. So this is an incredibly important parameter that we'll use. Well, all the things we talk about are important. And so if we wanted to, if we substituted this expression into here, we can calculate the capillary pressure, and it's going to be equal to for interfacial tension between the two fluids, the diameter of the capillary, the unit weight of the water, multiplied by the unit weight of the water, which is just this. 4 times interfacial tension divided by diameter of the capillary. And so that's an important parameter for us to understand. So we've talked about capillary pressure. We've talked about it being the difference between pressures in the wetting fluid and the non-wetting fluid. In this particular example, the wetting fluid is water, the non-wetting fluid is the air. There's definitely a difference in the pressures between them, and we now know how to calculate it in some straightforward way. And we will use this expression in the future to do that. And so this is basically the punchline, if you like. The capillary pressure is given by this expression, and it's proportional to the interfacial tension. Higher tension, the more pressure you have to push this stuff into the fluid, into the porous medium, and the smaller the diameter, the larger pressure you have to apply as well. Okay? So that's kind of the fundamental building block that we will use. So interest in using that, yeah, well, let's look at an application then of that rather than talking about this kind of esoteric stuff. And so how might we want to use that? Well, we can use that to basically look at how saturations change in a porous medium. And so this is kind of moving back from this capillary model to seeing how we might apply this. And we made the point before that most of the materials we're going to talk about in terms of aquifers are water wet. And so that means that they love water. Water loves them. Water loves the grains, basically. And so physically, a monolayer of water would love to cover all the glass that we have. In fact, that's the reason that it's kind of creeping up the side of this glass tube, because it just loves the glass tube and it just wants to physically go up. It's hydrophilic, right, rather than hydrophobic. And so in a water-wet sand, which is by far the majority of the materials that we'll deal with, this comes from Baer's book. It's written typically from a petroleum perspective. Oil is the dark fluid and water is the light fluid. And so if you're looking at a petroleum reservoir, then you start with the majority of the pore space is filled with hydrocarbons, black stuff. But what will be left there are some small pieces of water relative to these cross-hatched grains of sand. So these portions of water are present here. And actually what's also present here, it doesn't show because you can't see it, is that because the water loves the quartz so much, that there will actually be kind of a monomolecular layer of water which is in touch with the grain, that covers the grain, but is inconsequential other than that. And then there's a small pocket of water that sits here. And so this would be what? This would be 70%, no, this would be 80% saturation of oil, and it would be 20% saturation of water, and there'd be no gas in this. If you, bless you, if you pump water into here, which is how you get oil out, you don't just suck oil out, you have to replace it with something. So you suck the oil out and replace it with water, then you change the saturations to maybe 50% oil and maybe 50% water. You change the kind of topology, if you like, the connectedness in this pore space. And as you further pull out oil and you further put in water to replace it, you end up going from this, these look very different from each other, right? You have a little bubble, a bead of oil that's present within a sea of water here, whereas you had a bead of water here which is present with a sea of oil here. And this is called, the saturations of these change from what is called pendular saturation. Perhaps the terminology doesn't matter so much, to funicular saturation. And so pendular saturation means that you have a pendant of water in this particular case. Pendant of water in this particular case. You have, if you look at the shape of this water, it's almost like a donut, right? So you can imagine two ball bearings in contact or two grains in contact. The water really loves the glass, two glass balls in contact. The water really loves the glass. So it will exist as a monolayer covering both of these balls, but it will also be present almost like a donut around the contact between those. And that little bead of white material you have here is one side of the donut. There's another donut side you can't see here. There's another donut here you can't see here. Oh, you can best see it here maybe, right? Actually, perhaps you can't see it at all because it's too bright in here. So there's a ring. So there's a pendular ring that goes around this material, which is water, and there's a sea of oil otherwise. As you start replacing the oil with water, then all of a sudden this pendular ring disappears. It starts to take up the whole of the space within the pore space, and you end up then with this funicular saturation of water. And it's called funicular saturation because, like a funicular railway, right? Funicular railway is a cog railway, the one you go up the side of the Eiger on. It's got cogs on a track, and it winds you up as you go up. And so funicular saturation means that to be able to get rid of this this oil within the system, you have to physically drag it out with the water. You have to physically move the water, and the water has to grab onto it somehow, so it physically moves it out of the system. But basically, in this circumstance, you won't get any oil out of the reservoir. It'll stick there. And that's, of course, why petroleum reservoirs, when you pump them, you leave 40%, 50% of the oil in place, because you end up with this funicular saturation, which you can't physically get out unless you use some kind of method, enhanced oil recovery method, to be able to do it. And so that's relevant for groundwater hydrology problems because you know that this exists in different places within our plume, right? If we go back to this initial picture that we had of these chimneys, we said that you dump this stuff through the ground, it'll go here and it'll sit as a lens. So this will be almost 100% oil saturated. Well, it'll be 70% oil and it'll be 30% water in this zone, but it'll be largely the non-wetting fluid. And so this will be the top of those figures that we looked at. In this zone here that feeds that, it will be the opposite. There'll be some air, there'll be some water, and there'll be a few beads of oil as well that are left in the system. It's slightly different from the case. Actually, the better example is this, right? This is the case where it'll be 70% NAPL and 30% water. But up here, there'll be no air in the system, but there'll be little beads of oil in the system surrounded by a whole lot of water. And if you want to get this free product out of the system, it's almost impossible because you can pump the water and the water won't have enough velocity or pressure gradient in it to be able to pull this little bead of material from one side of the pore to the other, right? The only way you can get this little bead of stuff out is to have enough of a pressure gradient across this pore space that you squeeze it out through this space here. And it turns out that that's a lot of pressure you have to apply. And I guess we kind of know that because the pressure you have to apply is this capillary pressure. It's the same as pushing a bead of a fluid out of a straw. If it's a lone bead, a marble if you like, within the straw, is that for any given interfacial tension between the water and the oil, which is kind of set, if the diameter of this is very small, you have to apply a very big pressure to be able to get it out. If you can only apply a pressure which is due to flowing fluidness, which is not very large, then you're physically just not going to be able to move it out. And so perhaps we've rationalized one reason why it's very difficult to remediate sites beyond a few percent, because then you have to resort to other methods like allowing it to dissolve and then removing the dissolved plume by pump and treat, for example. Okay, so how are we doing? Okay, I'll do one other thing before I quit. So we've made the case that we can use this analog for a bunch of grains. We're interested in the pore throats, which are the controlling, the rate limiting step, if you like. They control the behavior in this being able to travel through the system. So we can represent these pore throats maybe as a bunch of capillaries of different sizes. Of course, that's not really the case. And what really is the case is that these grains look like this, a grain here with a grain here, and with this contact material which sits between them. And it turns out that you can do an analysis very similar to what we did in terms of looking at the difference between the fluid pressure between the air that sits here and the fluid pressure in the wetting fluid that sits here, and calculate what that difference is in exactly the same way that we talked about the difference as you go across this barrier, this boundary. And if you look at it for this arrangement, then you end up with a very similar equation, which is that basically the capillary pressure is equal to the interfacial tension. Instead of being equal to 2 times the interfacial tension over the radius of curvature, in this case it's the radius of curvature of 2 components. And these 2 components are, if you think about this little grain here, there are two radii, right? There's this radius here, and so this radius of curvature that exists here and on this side, which is this thing. But also as you go around the grain, there's a radius of curvature. I suppose it would be relative to this center point here. Well, it is relative to this, right? This radius R2, which is around the grain. And so instead of looking only at this very simple analog here where we said about the difference between the pressures as you go across this boundary, it's because you have this curvature. It's exactly the same condition in a porous medium, but the curvatures now are in terms of the curvatures of this meniscus here and also as you go around there. And you end up with basically the same expression as before, and that is the capillary pressure that you have to apply. Well, the capillary pressure, which is the difference between the pressure in the air and the water on this boundary, is given by a very similar expression where instead of this being the diameter or the radius before, it's the sum of 1 over the 2 radii. So it's very similar. And so the bottom line, the take-home message from today, is that we can use this very simple analog to be able to say something about the pressure differences we have to apply to be able to push immiscible fluids through a porous medium, either as a bunch of capillaries or as a bunch of beads. In this case, this radius is pretty close to the radius of the grains. And so, obviously, if this is a big piece of water, the radius of curvature, I guess, would be larger. And if it's a bigger piece of water, in other words, which is like, well, that's not true, right? This radius of curvature would be an infinite radius of curvature. If the water only filled it up to this point, then you'd have a really big radius of curvature. So anyway, the radius of curvature will change with the saturation. But usually, if we want to use these expressions, we often take this just as being the diameter of the pore. It really is the diameter of the capillary, or it is the diameter of the bead, but they're typically similar to each other. So we can use that as a ballpark calculation. And we can look at bundles of these capillaries to look at the kinds of pressures that we'd have to apply to push these fluids through a porous medium. And we can think about arranging these either as a whole bunch of capillary tubes, if I had another pen, a whole bundle of pens in series, where these pens might be wide and very narrow ones, in which case we could guess that if we had a whole bunch of narrow pens, the stuff would get hung up in these, but if we had a whole bunch of open capillaries, then it'd be happy to go through there, even if we put a small amount of pressure on it to push it through there. Or we could think of a whole bunch of capillary tubes in series. A big capillary tube, a little capillary tube, a big capillary tube, a little capillary tube, as in some way representative of a porous medium where you have a whole bunch of different pore sizes and in different sequences. And if we wanted to think of that as some kind of analog, you could imagine that a whole bunch of capillaries in series, a big capillary tube, small capillary tube, big capillary tube, small capillary tube, would have quite a different response, right? You'd expect that the fluids would get hung up in these little capillaries and they wouldn't be able to go any further because you wouldn't be able to apply enough pressure to basically blow it out of the system. But in this, you'd get some stuff hung up within the pore space and other stuff would be happy to go through. I won't turn the screen up on its side, but imagine that turned on its side. So you have it vertically, and then come back and then answer the question that we posed a little earlier, and that is, why? Why has it chosen to take this route through here, and it hasn't taken this pathway that's gone through that? It's answered, right? This is presumably a more open capillary, even marginally more open than these other spaces, and so it's happy to go down the superhighway, and it gets cut off at this particular portion here, and will never go through here. And so one of the hallmarks of these porous materials is that you get really spotty distributions of these materials in the vadose zone and also in the saturated zone, because a very small difference in the capillary entry, capillary diameters, chooses whether it will go here or not go there. And so it bifurcates and goes in all these different places. Okay. I like to talk. Any questions? No?